Welcome to AI Paper Podcasts. Today we're diving into a really fundamental question about us, about human intelligence. How do we, so effortlessly handle completely new situations?
Right, drawing on this huge amount of knowledge we all have, but somehow keeping our thoughts coherent and focused.
Exactly. It's a massive challenge for AI, and, well, this paper we're looking at offers a pretty fresh take. So for our quick summary up front, we're exploring a paper called Modeling Open-World Cognition as On-Demand Synthesis of Probabilistic Models. It's by Lionel Wang and colleagues.
And the core idea that our minds achieve this amazing flexibility using something they call model synthesis architectures, or MSAs.
Yeah, think of these not as like fixed programs, but as dynamic mental models built specifically for the task at hand on the fly.
And the paper proposes a computational method, combining large language models, LMs, for their massive knowledge retrieval,
with probabilistic programming languages, PPLs, like WebPPL, to build these coherent, bespoke models.
The key takeaway is that this hybrid approach, it mirrors how humans judge things much better than just using LMs alone.
Especially in really new sort of open world situations, it feels like a really compelling direction for understanding and maybe replicating human-like reasoning. Okay, so let's unpack that a bit for everyone listening. This term, open world cognition, what does that really mean? And why is it such a tough nut to crack, not just for AI, but even understanding ourselves?
Well, it really boils down to that human edge, doesn't it? Our ability to just pull in relevant stuff from this, practically infinite background knowledge we have.
And apply it coherently, even if we've never seen that exact situation before.
Exactly. Like, think about predicting traffic, you consider the time, the day, maybe construction you heard about, the weather.
Yeah.
It's a huge mix of factors.
Or figuring out why a friend seems off, or analyzing a weird play in a game. We're constantly synthesizing.
We are, and that's where traditional cognitive models, even good Bayesian ones, run into trouble.
Right. They're often great in specific, limited domains, predicting physical events, maybe some causal learning tasks.
But they're constrained, right? They usually can't handle new variables, things the model designer didn't anticipate.
And that's the core of the open world problem, isn't it? How do you deal with this potentially unbounded set of relevant factors?
Without getting totally swamped computationally, it ties into the classic frame problem in AI.
The idea that checking everything you know for relevance for every decision is just intractable.
Precisely. Humans seem to shortcut this very efficiently. And what's really interesting is that current AI, even powerful LMs,
despite being amazing at language,
they often struggle with this kind of robust, coherent reasoning, especially when things are a bit out of distribution compared to their training data. This paper tackles that head-on by suggesting minds synthesize models just when needed.
Okay, so this leads us to the core proposal, these model synthesis architectures, or MSAs. How do they actually imagine these working? They break it down into two computational subproblems.
Yeah, that's right. So the first one is synthesizing ad hoc models. The idea is the mind constructs these small, specific mental models. They call them ad hoc.
Ad hoc.
All right. And it does this by intelligently retrieving, or marshalling, as they put it, just a relevant subset of your background knowledge. Call it K prime, drawn from your vast total knowledge, K.
So you're not bringing everything to bear, just the bits that seem relevant right now.
Exactly. The goal is to get pretty accurate inferences, like P8, without the massive cost of considering all of K. You approximate based on the relevant slice.
Okay, that's step one. Build the focused model. What's step two?
Step two is reasoning within that model. Once you've got your ad hoc built, you apply standard Bayesian inference techniques and answer the specific question, but only within that limited coherent scope.
So PA ad hoc. Build the right sandbox, then play in it rigorously.
You got it. The analogy they use is like a legal team building a case. They don't review every law ever written. They pull the specific statutes and precedents relevant to this case, build their argument, their model, and then reason within that structure.
That makes intuitive sense.
And, connecting this to the bigger picture, it's not just mimicry. It's a cognitive hypothesis. Maybe this is how our minds actually operate.
A genuine proposal about mental architecture.
Yes, and the proposed implementation is clever, using LMs for their statistical power in retrieval and synthesis, and PPLs for their formal, structured reasoning. It's like a custom chip being designed for each specific reasoning task.
So let's get into the weeds a bit. How did they actually build this MSA? Using LMs and probabilistic programming, they talk about a staged synthesis process like a pipeline. Can you walk us through that?
Sure. It starts, logically enough, with parsing. The LM takes the natural language input, the background story, the observations, the question you're asking,
Right.
and translates it into candidate probabilistic program expressions. Think of it like turning plain English into structured code snippets, even if the functions aren't really defined yet.
So like, Faye and Ollie lost race 1 to Lane, and Jamie becomes some kind of structured representation condition lost, maybe.
Exactly like that. It creates a symbolic skeleton with placeholders for the details to come. Crucially, it's prompted with examples to guide this translation.
Okay, skeleton built. What's next in the pipeline?
Next is relevant background retrieval. The LM goes back and fetches additional relevant background knowledge from its general store, but only stuff that helps fill in gaps in the initial input.
So if the prompt was vague about rowing,
It might pull in something like, generally stronger athletes row faster, or rowing speed varies between athletes. It augments the initial background to make it richer.
got it. And at the same time, it builds a dependency graph.
That's right. Step 3 is the conceptual dependency graph. While retrieving background, the LM also figures out how the concepts mentioned relate to each other, like strength affects speed. This graph provides structure and coherence, which is really vital for the next step. It helps ensure the pieces will fit together logically. Getting this graph right significantly boosts the quality of the final model.
So you parse the input, enrich the background, mapped out the dependencies. Now you actually build the model.
Now you build the probabilistic model. Step 4. Using all that structured information, the LM synthesizes the full symbolic probabilistic model in WebPPL.
This is where it defines those placeholders from step 1.
Precisely. It encodes the priors, the causal links, defines all the functions. You end up with a complete executable probabilistic program, ad hoc.
Ready to run, which leads to the final step.
Probabilistic inference. Step 5. You run standard Bayesian inference algorithms. They use things like rejection sampling on this freshly synthesized model.
And out pops a probabilistic answer to the original question.
Exactly. And this multi-stage process, the interleaving of LM generation and structuring at each step is really key. It allows for progressive refinement, and using WebPPL gives it the power to handle complex relationships and do rigorous inference within these custom-built worlds.
Okay, so they built this sophisticated MSA. How do you actually test if something like this behaves like a human? They came up with this domain, the Model Olympics. Sounds fun.
It is pretty clever. The Model Olympics involve these little stories, vignettes about athletes competing in sports.
Why sports?
Well, sports are naturally open world, right? There's intuitive cause and effect, strength impacts performance, maybe someone gets injured. There's uncertainty, lots of hidden variables like fatigue or natural talent.
Makes sense. What kind of sports?
They use 3. Tug of war, which built on some previous research. Then canoe racing, similar causal structure, maybe, but a novel setting likely not heavily represented in LM training data.
Ah, testing generalization.
Exactly. And finally, biathlon, which is quite different, involving both skiing speed and shooting accuracy. Different kinds of variables.
And how do they capture the human side of the comparison? Just ask people for answers.
They used a really neat method, a multi-sample judgment interface. Instead of just giving one answer, participants clicked 5 times on a scale for each question.
Oh, to represent their uncertainty, like drawing samples from their internal probability distribution.
That's the idea. It gave the researchers full distributions to compare, not just single point estimates, much richer data. People answered 8 related questions per scenario, testing for consistency.
Clever. So how do they systematically test the flexibility aspect?
Through 3 experiments, each getting progressively harder. Experiment 1 had detailed background info. All the key causal links and relationships were spelled out explicitly, the most constrained test.
Good.
Experiment 2 used underspecified backgrounds. The language was vaguer. Participants and the models had to kind of fill in the blanks using their general knowledge.
More like real life.
Definitely. And then experiment 3 was the real open world test. They took those underspecified stories and added extra details sourced from other people, like snippets of sports commentary.
Go on.
Things like, oh, Taylor's totally new to this sport, or, Avery seems to have a stomach bug today, or Kay pulled a muscle earlier.
Wow. Okay. So truly arbitrary, novel things thrown in.
Exactly. Variables and dependencies the system had never seen explicitly structured before. And crucially for this experiment, there was no handcrafted symbolic model baseline.
Why not?
Because traditional fixed models simply couldn't handle integrating those kinds of arbitrary new variables on the fly. Only the synthesis approach could even attempt it.
All right, the Model Olympics are run. What did the scoreboard say? How did the MSA stack up against human reasoning and against the other AI approaches?
Well, the results were pretty compelling. Finding number one, human reasoning in these scenarios looks pretty Bayesian and, importantly, MSA-like. Meaning the MSA's judgments showed high correlation, good R-squared values, and low Wasserstein distances compared to the human judgments. This held across all three experiments.
Even the really tricky experiment 3.
Even experiment 3. Often, the MSA's judgments fell within the 95% confidence interval of human-to-human agreement. So it suggests people are reasoning consistently with Bayesian inference in dynamically built models.
And it showed these models could be synthesized from language, not just hand-coded.
Right. X1 showed synthesis worked in detail. X2 and 3 showed it generalized powerfully, validating that core hypothesis even when information was sparse or totally novel.
Okay, so MSA looks human-like.
Yeah.
How did it compare to the LM-only alternatives?
That's the second key finding, and maybe even more telling. People's reasoning was significantly more similar to the MSA's structured inference than to the LM-only baselines.
Especially when things got weird.
Especially when generalizing to those new details, yeah. And remember the Canoe Race.
The novel context one, yeah.
Despite having a similar causal setup to tug of war, the LM-only model struggled more with the Canoe Race. The thinking is, Canoe Racing just wasn't as common in their training data.
So the LMs could retrieve facts, but struggled to weave them into a coherent causal model for this less familiar scenario.
Exactly. It highlights that LMs are amazing retrievers, but maybe less adept at building that local coherence needed for robust reasoning in new situations. Humans and MSAs, using explicit structures, handle that better.
You mentioned something earlier about LMs being oversensitive.
Right, that was another difference. LMs sometimes overreacted to single surprising events. Like if a supposedly fast runner had one bad race, the LM might drastically lower its estimate of their overall speed.
Flipping its assessment based on one data point.
Kind of. Whereas humans and the MSA, with its explicit priors and causal model, integrated that surprise more robustly. They'd update, sure, but not throw out everything else they knew.
More stable reasoning.
And just to hammer it home, Experiment 3, with those participant-generated novel details, the MSA was way better than the LM-only models. That's critical because traditional models couldn't even play in that game.
So the ability to flexibly recombine symbolic causal knowledge seems absolutely key for that kind of open-world generalization.
It really strongly suggests that, yes.
Okay, so this MSA approach seems incredibly promising, fits human data well, especially in novel situations. But it's research, it's not perfect yet, right? What are some of the limitations they noted, and where does this go next?
Absolutely, it's not the final answer. One thing is, well, human data itself is noisy. Perfect fits are hard.
Sure.
Also, the MSA judgments sometimes seemed a bit smoother or more spread out uncertain than people's. Maybe the synthesized models weren't diverse enough, or humans sometimes make sharper, more confident leaps.
Interesting. Anything else?
A key one is that the LM-guided synthesis, while powerful, still had trouble sort of inventing new primitives or complex abstractions without seeing examples first.
Like the pulled a muscle in a previous match example. It needed a hint about temporal logic.
Exactly. It couldn't quite make that leap without an explicit example in its prompt, so it's still somewhat guided by, maybe limited by, the examples it's shown. There's room for more generalized abstraction capabilities.
Okay, so limitations acknowledged. How do we push this forward? Where does the research go?
Well, the authors frame this as a small step towards tackling the huge challenge of open-world cognition. The future seems to be about exploring a much wider range of possible MSAs.
Like using different underlying technologies.
Yeah, maybe using other modeling languages better suited for things like long-term planning or reasoning about multiple agents, or exploring different ways to synthesize the models, maybe refining them based on feedback.
Or letting the MSA itself learn over time.
That's a huge one. Allowing the system to learn from its successes and failures, perhaps adding successful new concepts or structures to its own modeling toolkit, augmenting its language.
That sounds really powerful.
And the ultimate goal, the really provocative thought here, is that maybe a deep understanding of human open-world cognition is actually becoming reachable now.
Right.
By systematically building and scaling these kinds of MSAs and rigorously testing them against human behavior, maybe we can finally start to figure out which models of general human intelligence hold water and how all the different cognitive pieces, fit together.
That is a truly profound vision. Okay, so wrapping up our deep dives today, we looked at this fascinating idea that our minds might build custom mental models on the fly to handle novelty.
And how this hybrid AI approach, blending the knowledge retrieval of LMs with the structured reasoning of PPLs, seems incredibly promising at capturing that human ability.
Especially for reasoning coherently in these messy, unpredictable open-world situations we face all the time.
It really underscores the potential power of combining statistical learning with explicit symbolic representations for achieving that human-like coherence and flexibility.
So maybe next time you find yourself facing something totally new, take a second to appreciate your own internal model synthesis architecture, how you pull together relevant bits and pieces to make sense of it all.
It's pretty amazing when you think about it.
If you want to dig into the technical details yourself, the paper is Modeling Open-World Cognition as On-Demand Synthesis of Probabilistic Models by Lionel Wong and his colleagues. Definitely worth a read for those interested. Thanks for joining us on AI Paper Podcasts.